In this video, we're going to introduce the notion of infinite series, and this is section 11.2. So infinite series is a sum of the terms of an infinite sequence. So if we have some infinite sequence a sub n, then we can talk about the infinite series associated to that sequence. Here's an example of what an infinite series might look like. 1/2 plus 1/6 plus 1/12 plus 1/20 plus 1/30, so on and so forth. Let's see if we can figure out what the sequence is this is a sum of terms for. So it looks like here I'm adding at the nth step. This term was 1 over 1 times 2. This term is 1 over 2 times 3. This term is 1 over 3 times 4, 1 over 4 times 5, etc. So it looks like at the nth step I am adding 1 over n times n plus 1. So there's special summation notation we use for series. So I can write this series as the sum, n equals 1 to infinity, of the generic form for the sequence that's associated to it. So 1 over n times n plus 1 would be a way of writing this series. Here are some other examples. 1 plus 2 plus 3 plus 4 plus 5 plus so on and so forth. So at the nth step we're adding the number n. So this is a sum of every single counting number. We could write that as the sum, n equals 1 to infinity, of n. We have the sequence made up of terms 1/3 plus 1/9 plus 1/27 plus 1 over 81, etc. So notice at the nth step we are adding the nth power of 1/3. So as a sequence, that's the sum, n equals 1 to infinity of 1 over 3 to the n. Let's do one last example. 1 plus 1/4 plus 1/9 plus 1/16. This is the sum of 1 over n squared from 1 to infinity. Now if we look at all these series, so these sums of the terms of sequences, a lot of them have the sums of terms that are getting smaller. So in these three cases, we see that the general term is shrinking, the extra bit I'm adding on. So you might ask yourself, if I add up all these terms, am I going to get a finite or infinite sum? This one, where the nth term I'm adding is getting bigger and bigger, it might not be too hard to argue why this sum must be infinite, because the piece that I'm adding on is getting infinitely larger. But the question is, what about these three? Which of these infinite sums are finite? And because we know it's possible for the area under the curve of a function moving all the way out to infinity to be finite, there's a chance that it might make sense that these sums could be finite. Now, I have to note a couple things here. We don't have a way to actually add infinitely many terms together. We can't actually keep adding till infinity. There's not enough time. So in order to figure out if these infinite sums are finite, we're going to try to look at a sequence of what happens as we add additional terms. How does the sum grow? So since we can't actually add up infinite sums, in order to determine if one of these sums is finite or not, what we'll do is look at how the sum grows when the finite sums are considered, just adding one term at a time. And so this is the notion of considering the sequence of partial sums of a series. And we call it a partial sum because we just take the first k terms. And we'll see if the sequence converges. So let's look at a couple examples using Desmos.